So time for the demo of our hybrid cloud platform. So in this demo we're going to focus on three things. So first, hybrid cloud infrastructure. At this moment it's not hybrid cloud yet. We're only processing locally on our own private cloud, but during the demo we will spill over to Amazon. As you can see, the metrics here on the second row are flatlining because those are the Amazon metrics and there are no machines on Amazon except for the VPN endpoint and the DNS server. And we're also going to talk about monitoring, which you can see on the walls, and the automated deployment, of which you can see a very little bit on the last screen. As a general guideline for this presentation, if you have any questions or want anything clarified, please ask me, because I prefer dialogue to monologue. So what are we going to show? We're going to show the workflow, a workflow that is somewhat based off the unified post case study. So we have three stages in this workflow. First, we have pre-processing, so we take in a database or a CSV file and we split it into independent documents. These documents are rendered in parallel. So first we apply a template and then we render this template to a PDF. All these PDFs are joined together, then they are packaged in a single zip and archived to disk. So this is also the dashboard you can see in the middle. So if we look at the logical decomposition of the entire system that's running now, so we have a hybrid cloud, we have some virtual machines here, we have some virtual machines on Amazon, and the two networks are connected with the VPN. Top of that we have basic infrastructure services like Java runtime environment, Cassandra for storage. Top of that we have the dreamaas middleware, of which we've already seen something in Massimo's demo, with the application API and the coordination model. And on top of the API we've implemented several workers. So first we have the CSV to task worker, the templating worker, the rendering worker, and then we join everything together and zip it. These workers are our unit of development, but they are not our unit of scaling. So we scale them in packages. So we have the pre-processing package, we have the rendering package, or as we say, a task worker because it corresponds to a virtual machine type, and post-processor, which is the last task worker type. If you look at how it is deployed, so currently we don't have this part, we only have the Distrinet cloud part running now. Here we have the centralized monitoring collector, which collects all the data. We have the central configuration master, which manages all the other machines, which itself also runs in a virtual machine. It manages itself. Then we have the three types of task workers. So on top we have the pre-processing, here we have the rendering, and here we have the post-processing. We also have one special coordinator task worker, the master, which exposes the API to the system, so we push work in via that worker. It also contains a simple scheduler, and that's kind of it for our local cloud. In a few minutes we will spill over, and we will only spill over the rendering node because that is the most CPU intensive part of the pipeline. So we will spill those over to Amazon. So as you can see, the system is under continuous load. We have a load generator that randomly adds work and tries to maintain an average of 25 jobs running at every point in time. And each job is between 100 and 1000 PDFs. The numbers you see in the queues, these are tasks, and a task is a package of up to 100 PDFs. So the throughput in the top graph is not throughput in PDFs per second, but in hundreds of PDFs per second. On the bottom you have the actual throughput of PDFs per second. So now we are only in one cloud. Soon we will scale out to Amazon. First I'm going to explain what we see on the dashboards. So we have the dashboards in different abstractions. Here on top we have raw data. We have memory usage per machine, we have CPU usage per machine, we have the 1 minute load per machine. Here on the top row we have exactly the same data but aggregated per worker type. So then we see for the three worker types plus the master server aggregated, so then we can directly see, for example, the purple line on the top. The rendering has most memory available. It also consumes more CPU than the others, and it also has a higher system load. So from this graph, we can immediately see that the bottleneck of the system is the rendering stage. And here we have metrics at an even higher level. Here we have application level metrics. So in the arrows, we see the size of the queue between the workers. In the worker, we see the throughput and the latency for this specific worker type. On top of the workers, we see the CPU usage and the network input for this specific worker type. And on top, we see the name of the worker type plus the number of instances we have currently running. So now that we have seen how it works now, we're going to scale it out. So I have here an additional dashboard which tells us how many machines we currently have and how many machines we have requested. I'm going to refresh it. So we have 0 machines requested in the Amazon cloud. So now I can click here. I can say let's add 5 machines. And now I click on OK. And then soon we will see the imp agent starting to create new machines on Amazon. But this is a process that might take some time. So I'll continue the presentation. And if something important happens, then Bart will tell me to tell you. So now currently we're spilling over, so new machines are being created. As new machines appear, the data streams are automatically incorporated into the dashboards. This is a property of the system. Every type of data we capture is all piped towards a central database and stored there. So if we would have an unexpected machine appearing, we would also see it in the graphs. So while we wait, I'm going to take a step back and look at the system from a higher level. So we actually have a closed loop control system. So we have our actual system that is running, which is being observed by a monitoring system, as you can see on the walls. The scheduler can look at the monitoring data and make decisions about how to scale the system. It can. Now I have played scheduler. I added the number of machines myself, but an automated scheduler can do exactly the same. He can then give this information to the configuration management system, which will then start creating new machines. So no new machines yet. So the configuration management system that pushes out all the data is called IMP, the Integrated Configuration Management Platform. It's a framework we've developed here in basic research track. And it's a system that makes abstraction of heterogeneity. It creates high-level models that make abstraction of technical details. So it allows us to specify things at the architecture level. Like we can say, we want 5 virtual machines, and the first one is already appearing. And we don't have to say these machines need to have these IP addresses, or we don't have to say these machines have to be interconnected in this way or that way. All this low-level stuff is handled by the framework. We only have to define at a high level. Second big advantage is that the build of the system internally is very modular. So we define certain abstractions, like we define a cloud computing platform. And then we can plug in different implementations, like we can say we have an OpenStack, or we can say we have an Amazon. And all the layers built on top of it remain unchanged. So this allows us to spill over very efficiently, because we don't have to redo all the configuration. We only have to do a little part of the configuration. The second part I want to focus on is the monitoring, which is done by Monarch, monitoring architecture. Monarch is also a system to make abstraction of heterogeneity, but then not to define systems, but to inspect them. So Monarch is capable of making abstraction of data. As you can see there, there we have individual machines, there we have task workers, and there we have the actual application level. So if we look at how it works, what it looks like, So on every machine in the system, we have a collector agent called Flens deployed. This agent can load into itself different adapters for different protocols. Then we can connect different sensors to it. For example, we use an existing sensor suite called Collecte. It's deployed on every machine and it collects all the system level metrics. This data is piped into the local collector, which will then forward it onto the central system. We also have a Flens, so a collector deployed inside the dreamaas middleware. So all the application level metrics are reported internally to the internal collector. Then we have added some configuration that connects the internal collector to the machine collector, and as such the data flows into the central system. On the central system we have the collector and we have an aggregation engine. This is a complex event processing engine that allows us to do pattern matching on the event streams, and that allows us to combine different streams into one stream. Then finally, all the data, both the unaggregated and the aggregated data, is stored into Graphite, which produces the nice dashboards you can see on the wall. So how far are we with the scaling? So we have the machines, but
now the new render servers are fetching that configuration.
Yeah. So do we already see? No, we don't see the traffic of the configuration operation yet. So now we have the machines, but now the configuration management platform has to add all the configurations. So we start all the machines as base images. They are all identical and they are customized, each to its own unique configuration. So we already see a little spike in the outgoing VPN traffic. But the machines are still coming up, so it'll take a little more time. So back to the Monarch, the monitoring framework. What's the nice things about it? So if you are a programmer, Monarch is a very convenient abstraction. So we're deploying. So it's a sink into which you can pump all kinds of data. It can collect metrics, it can collect logs, and it's present on every machine. So you have a local collector on every machine. So for a programmer, it's something that's always there. You can put all your data into it and it will eventually go somewhere. For an operator, for a system operator, the big advantage of Monarch is that you only have to manage one management data pipeline. So you don't need some configuration for the application monitoring, different configuration for the system monitoring. Everything is uniform and the administrator doesn't even have to know which data is going through the pipe. Only when you have performance issues, then you have to start tweaking it. But it's much easier to maintain. Then for an analyst, so someone who wants to analyze the data, it's very easy that you have a unified data pool. All the data is in one system. The system itself contains the engines for the aggregation. So you have instant access to data, which makes comparison of different levels of abstraction very easy. And then the last and perhaps the best thing, in the current dreamaas platform, IMP completely manages Monarch. So if you deploy this platform, all the monitoring is there, up and running. So you basically have that for free. So how are we with the scaling? So now we see the VPN traffic spiking up. That's because we're starting to pump configuration data over to the other side.
If you see the IP addresses with 31 and 59 or the virtual machines that run on Amazon, so they're still fetching that configuration and installing software.
So I'm going to perhaps go deeper into some of the specific dashboards. So there we see the number of rendering nodes shot up to 7. So we now also should start getting some metrics from Amazon. So we're slowly getting there. But I'm first going to continue my explanation about this dashboard here. So on every one of the collectors on the machines, we also ran a very small micro benchmark every 10 seconds. Because in the cloud, you're never sure of the performance of your system. So we were lucky, and our cloud had a huge performance spike. So this number, the higher it is, the slower the machine is. So here we see, somewhere an hour ago, this benchmark suddenly took a lot more time. And at the same time, the CPU usage of all the nodes spiked down. So it seems that our CPU just didn't get enough cycles, which is, well, it was quite interesting that it happened just now. It's probably thesis students running their final benchmarks. So this kind of combination of different metrics can give us very interesting insights. As we see here now, here we get some metrics for Amazon. Well, I think I covered the most important aspects. So any more questions?
Regarding the bottleneck is moving into the join. That's what I'm reading.
Well, if you look at the throughput or the latency, we see that the biggest latency is in the rendering. It has 5.8 second latency. So this is, if we would fill the pipe and keep it filled the entire time, the bottleneck would be here. Because it's the slowest station in the queuing station, so everything will get stuck there. But because we're not in a steady state regimen, we push in a very uneven load. We see the bottleneck moving through the system. But if we would get it balanced and to steady state, then the bottleneck would be the render node, but we're not in a steady state, which also makes it quite hard to do control and scheduling.
The join nodes, the join worker is a worker that performs many queries on the storage system. So we added workers at Amazon, and they increase the load on the storage system. So every more queries a worker has in the storage system, the more it is affected by that we're not symmetrically scaling the platform anymore. We're only adding workers that add load in the storage system and not scaling up the storage system. That's one of the reasons we will see that the join worker will be queuing up. You can also see that in the graphs for the latency for the tasks for each cloud in the second way.
A small question.
Yeah.
Imagine a change request where people say we want to monitor other properties, and then those other decisions plug in backend algorithms too. If you need to reconfigure the monitoring part and the reconfiguration part for the sake of another algorithm, can you give us an estimate in terms of effort that would require?
Well, I could give you a small run through about the changes we have made for the specific dashboards of the PDF rendering throughput on the bottom. So initially our workflow platform didn't have batching support. We did one PDF per task, but it was more efficient to batch the PDFs together. So now the throughput metrics are in terms of tasks and no longer in terms of PDFs, but PDFs is the thing we're interested in. So we wanted to add this metric, and the specific change we had to do to incorporate this metric is the following. So this is the code of the actual renderer, and here we had added a line of code which just says start a timer called worker.work pdf.render, and at the end when the rendering is done we just stop the timer. This is
And everything else is required by the framework.
Yeah, this is everything we had to do because this metric is collected in exactly the same way as all the other middleware metrics, so that infrastructure was already there. It is also aggregated in exactly the same way as the other middleware metrics. So everything else was basically for free.
From dreamaas.
What?
From dreamaas.
Yeah, that's of course.
Okay, thanks.
I think for the rest of the day you'll see these graphs evolving with metrics from Amazon. I think now is the time that we can go to the application.